Okay, so the last apportionment method that we're going to talk about is Huntington Hill method. Um, I can use the same example with the Congress of Parador again. So I left this up from Webster's method. So I'm going to read this one slide right directly from the PowerPoint just to give you an idea of what's going on. It says Huntington Hill method. The method was first proposed by American statistician Joseph A. Hill and later revised by mathematician Edward B. Huntington. The Huntington Hill method is a sophisticated variation of Webster's method, and in many cases it produces exactly the same apportionment as Webster's method. That's the part that I really wanted to point out. At the same time, the two methods are not equivalent. You're going to see that they're different. And in some cases, they do produce different apportionments. So if you read this literally, it seems like they're saying that a lot of times using this method will give you the same exact apportionment as Webster's method, but it doesn't always do it. But usually it does. That's what I'm getting at. So we will give examples of both of these situations. Well, I'm not going to give an example of that. I think they show a method, or they show an example where using Webster's method and Huntington Hill, you get the same apportionment, and then they do another example where you don't. So it's not that interesting. You can look at it. It's in the PowerPoint. So everything about Huntington Hill is the same as Webster's method, except for how you round. So I'm going to talk about, I'm going to write it out, even though, like I said, you can read about it. You should be reading about it. Huntington Hill Rounding Rule. Can you see it that right? Oh, you can see the whole thing. I should see where you can make a line right here. Oh, I was going to say I don't want to write below that line because then you might not be able to see it. So Huntington Hill Rounding Rule uses this thing called the geometric mean. So if you have two numbers, A and B, so let's say we have two numbers, A and B. I know those aren't numbers, but in general, let's say these represent two numbers. The geometric mean of those numbers is found by taking the two numbers and multiplying them together and then taking the square root. Okay? So for example, if you had like 10 and 12, the geometric mean would be 10 times 12, take the square root of it. So it would be the square root of 120, whatever that is. It's about 11. Not exactly 11 because the square root of 121 is 11. So it's a little bit less than 11. So how you're going to use this is that when we get numbers like this, 32.92, we're going to take the lower quota, which would be 32, and the upper quota, which would be 33, and find the geometric mean. So, using UNL now, you can say the geometric mean, or the cutoff for rounding, I'll call it C. The cutoff for rounding these numbers is going to be the geometric mean of the upper and lower quota. Okay. So if C is greater than the quota, then you would round down to L, and if it's greater, then you'd round up to U. We're going to do an example so you see. So, for example, let's do this one because it's small. the lower quota would be 3 and the upper quota would be 4. Can't forget the radical. So hopefully I brought my calculator because it's kind of hard to do square roots in your head. Pretty sure I had the calculator because I had it here yesterday for something else. So let me just figure out what the square root of 12 is. It is 3.4641 approximately. I'll just write 3.46 because it's approximate anyway. So if this number is below that, you'd round down. If this number was above 3.46, you'd round up. Well, this is below it, so you'd round down. So that's the only difference between this method and Webster's method. We're still going to have to tweak this probably to get a suitable divisor, and then instead of using conventional rounding like Webster's method, we're going to use Huntington Hill Rounding Rule, which tells you to find the geometric mean of the upper and lower quota. And then you use this number as a cutoff. If your actual number here is below that, you round down. If it's above that, you round up. So let me write down the steps. I think I have the steps written down. Yep, I do. So for all these methods, knowing what the steps are is pretty important. I just don't want to erase this, so I'm writing everything over here. I think I don't want to erase that. Let me see if I use that same chart again. Yep, I do. Sort of. Alright, so the steps, so I'm going to just write HH, Huntington Hill method. So step 1, find a suitable divisor. Now, like I said, you should be reading book, PowerPoint. There's also videos on my math lab. So you can watch this video, but there's probably a video on my math lab. If anybody has any questions about how to look at those videos, you can probably figure it out yourself, but if you have a question about it, I'm going to be holding virtual office hours. Plus, if you call my office phone now, it forwards to my cell phone, so if you have any questions, probably limit that to only call me during the week and like maybe from 8 to 10 at night. And only if you have a question, obviously. Let's see. So what this means, and this is why you should read, but I'm going to explain it right here. What does it mean to be a suitable divisor? Well, it means when you divide every state's population by D and get these numbers here, and then use the Huntington Hill Rounding Rule, you want it to come out to be 250 seats in this example. So if you pick D and then round, if you pick D and then get all these numbers, and then when you round using the Huntington Hill Rounding Rule, if it doesn't give you the 250 that you want, then you can't, you have to pick a different divisor. You keep picking different divisors until when you divide by D, you get numbers here that when you use the Huntington Hill Rounding Rule, gives you the number of seats that you want. So then step 2, use the Huntington Hill Rounding Rule. Okay, those are the only 2 steps. I mean, those are the 2 steps, but in each step there's sort of unspoken steps. Like I said, the steps to finding a suitable divisor D are knowing that that D has to be a number that when you divide each of these numbers by it, you get numbers here that when you're going to do step 2 gives you the right amount of seats. And I think in using the same example with the Parador Congress, I think you're going to start with the standard divisor again. So since the population is 12.5 million and we have 250 seats to apportion, the standard divisor is 50,000 because it's this number divided by that. So you're going to divide each state. So you can start with the standard divisor just like you did in Webster's method. So you're going to start with dividing by this. We're going to say, oh, I hope that the standard divisor is a suitable one. So you're going to figure out all these numbers. And then you're going to use the Huntington Hill Rounding Rule. Okay, so let me write cutoff. Maybe I'll show some of the work over off to the side. So the cutoff for this is you have to take the geometric mean of the lower, which is 32, times the upper, which is 33. 32.92 is in between the two numbers, 32 and 33, the two integers. So I'm going to say 33 times 32 is 1056. So I want to know what the square root of 1056 is. It's 32.496, approximately. 32.496. Okay. Now, it's a trend that they do. They always do it to 3 decimal places, I've noticed. Obviously, the number is actually bigger than that. It keeps going. It's 0.496, 15362, and it keeps going, but my calculator stops there. Okay, so, and then for this one, you would do the square root of 138 times 139. I'm not going to show you all those, but I'm going to just write down all of the numbers here. I've noticed that a lot of these numbers come out to having like 0.4 or something. That's the difference. Like conventional rounding, if this number was greater than 41.5, you go up. If it was less than 41.5, you go down. Here it's the cutoff. Instead of 0.5, it's 0.497, which is pretty close, but it's a different. So like I said, these numbers here come from taking the geometric mean of the upper and lower quota. So what you're going to do now is round using the Huntington Hill method, which means we're using these numbers as the cutoffs. So since this number here is bigger than that, you go up. Same here, this number is bigger than that, so you go up. This number is smaller than that, so you go down. This number is bigger, so you go up. This is bigger, so you go up. Bigger, so you go up. So what happens here if you add all these up? You get exactly 250. So this works. We don't have to tweak the divisor. The standard divisor was a suitable divisor. So what would happen if this number was like 251. Well, then you do the same thing we just did in the video I showed you on Webster's method. You would make that number bigger, which will make all these numbers smaller, which would probably change, well, it would change, it might change these depending on how much bigger you made it. So, like I said, if this came out to 251, you'd make that bigger. That would make this go down. So you might go down too far though, then you would make your standard divisor a little bit less. In other words, you just have to tweak it until you get these numbers here, when rounded using the Huntington Hill Rounding Rule, give you the right amount of seats. It just so happened that the standard divisor worked here. So I don't know if I have another example where it doesn't work. I could make up an example, but like I said, I wanted to keep videos in between 10 and 15 minutes. And this video has just gone over 16 minutes. So make sure you read about it. There's a couple homework problems on the next homework assignment where you have to know how to do this. It might be the fact that the standard divisor actually just works. But if it doesn't, like I said, you would do what we just did with Webster's method. You either make that number bigger or smaller, depending on if you want to go up or down, if you have too many or too few seats. So remember, you can get in touch with me, email, call my office. I'm going to probably post announcements this weekend, tomorrow maybe, or tonight, on when my office hours are going to be. I think I might have already done that, but I think I might have to change the time. I'm not sure. So they're going to be virtual office hours. There's a program called WebEx that I can basically Skype with multiple people at the same time. So that's how I'm going to do my office hours. And if you have any other questions, like I said, email, call my office. And I'm going to post about this too, we might actually have at least one class in between, like an online class, where everybody comes in the room at the same time on my WebEx virtual classroom. And we might have one class before the next test, which will be on April 10th. And the test obviously is going to be online. So, all right. So I'm going to try to make other videos for later on. I don't have to do it. I don't have to post them right now, but for Chapter 6 and Chapter 8, which are the only other chapters that we're going to cover. So just keep your eyes open for those, and like I said, if you have any questions, email or call me.